Next up, we've got our very own Timur Dumla, who's a member here on the Juice team. I'm sure most of you have met him by now at the conference. And Timur's going to follow up his wonderful CPP Con talk, which he did about basically threading problems in audio. And he's going to come on to the next stage of that, which is talking about floating atomics. So, Timur Dumla.
I have to apologize to you, so I'm not going to go meta, and I'm not going to show you any cool apps. And I can't tell you any stories about the 80s either. I'm really sorry. I'm going to talk about C++ code. So bear with me. So I did this talk at CPPCon about, as you said, threading problems in audio code. And people were asking me to do a follow-up talk. And I thought, that would be really cool. I could talk about some other big topic in audio like SIMD, or like there's a few other topics that you could do such a talk on. But then I realized I only have 20 minutes here. So I have to sort of focus maybe on one thing. And then I decided just to drill down a little bit deeper into one of the topics I covered at the last talk. And I'm going to talk about floating atomics. So this is really more like specific about one specific problem or one specific thing that you should be aware about if you write multi-threaded real-time code. So I'm just going to say something about why we need atomics in audio code and go a little bit through the interface of std_atomic for those of you who are not very familiar with it. And then if you're using that with floats, there are some specifics that you should be aware about, so I'm going to talk about those. And then I'm going to have a practical use case, which is actually about an existing Juice class, which is the smooth linear value one. So apply this to like actual real-life audio code. So this is sort of the general overall topic. That's the problem that we're facing in audio code, is that we typically have some kind of multi-threaded setup here where we have a high priority real-time audio thread, which gets like a real-time audio callback and computes some audio. Then typically we have a GUI thread, which is running a message loop. We receive messages from the GUI. Then maybe we have another thread catching MIDI or OSC input from some kind of hardware device. We have another thread that may be reading or writing stuff from disk. I'm just seeing that it's a little bit cut off here. I hope it's not going to be a problem. So we have all these different threads, and you have to worry about synchronizing them properly. And you want to do it in such a way that the audio thread doesn't block so you don't get any audio glitches. So this is sort of the overall problem that you're facing. And I'm really going to talk about really just one super simple use case. It's probably one of the first things that you do if you write an audio plugin. Is basically the use case is you have a single knob or a control that controls something like a level or another parameter, which is just a floating point number, and that should directly affect your audio callback. Basically, in this example, if you turn the level knob, it should adjust the level of your audio. So that's it. That's the use case. And here's the code for that. Really simple. You have an audio callback where you generate some audio, doesn't even matter what it is, and you multiply that by a level. And then you control the level from the GUI. So whenever the user turns a knob, you receive a callback here. And you change the value, and then you use the value down here. And all right. Super easy, right? So what's the problem with this code? Yeah. There's a race condition here. So, but you could say, it's just a float, right? So what could possibly go wrong? It's fine. Everybody's doing that, right? So but it's a race condition. What does that mean? Race condition means you fail to properly synchronize access to the same data from different threads, so you can get torn reads and writes. You can get some in-between state. It won't happen to you with a float probably in that code, because on most architectures, reading and writing a float is a single instruction. But what if you have a double or an Int64 and you compile it for a 32-bit plugin? Is that still maybe? Then if you don't have any synchronizations, then the compiler can optimize your code. It can change stuff. I'm going to talk about this a bit more in detail. You don't know if you change the value from one thread when the other threads are going to be seeing this. We have like caches and the CPU and all this kind of stuff. You don't express your intent anywhere. You don't say this is actually concurrent code. So that's a problem as well. And then most importantly, the C++ standard says, if you have the same data that is written by one thread and read by another thread simultaneously, that is defined in a C++ standard as a data race. And a data race is defined as undefined behavior. And undefined behavior, so what does it mean, undefined behavior? It means it could work just fine, or it could crash, or you could get some really subtle, maybe stack corruption, or one of these favorite situations. I'm sure you all have seen this in debugging, where like some variables magically change their value and you have no idea where this is coming from. And maybe like the actual bug is in a completely different part of your code. Or actually your computer could catch fire and explode. And that would actually, this behavior would be consistent with the C++ standard, right? It's undefined behavior. So to go a little bit more into like the actual sort of language compiler level, in C++ 98, we had this as-if rule, which means also, so if you don't do any synchronization, you just have plain C++ code, the compiler is actually going to do lots of stuff with it. The optimizer can reorder your instructions, it can replace one read or write of variable with two reads or no reads at all, it can optimize variables out of existence, it could put like two variables in the same address if they're accessed from different places, even in the same function. It could mess with your code as much as it wants. And the only guarantee you have is that sort of the program that results will execute as if it was the code you wrote, with one exception. Anybody knows the exception? So the exception is if you have return value optimization or copy elision, and then it's allowed to optimize away a copy constructor, even if that has side effects. So that's an exception. But otherwise, as-if rule. So now in C++ 11 and 14, we have this other thing which is called memory, the memory model. And I could talk 1 hour about the memory model. Unfortunately, there's no time for that. So really quick, it says sequential consistency for data race-free programs. It means that the compiler optimizer is allowed to do all that stuff that I just mentioned. And your program will still execute as if it was some arbitrary thread interleaving off the code that you wrote. So it's aware of the fact that you can have multiple threads. So this is sort of the constraint that compiler writers are really doing a good job to sort of guarantee you that this behavior will still be, like your program will still do that. So you can still reason about the code that you write, even though the optimizer may mess with it. But this only holds if it contains no data races. Otherwise, the behavior is undefined and everything could break. So in this very simple example, let's say you want to make this defined behavior. So what do? You can insert mutex, but then you're blocking, right? You have a lock in your audio thread. And this is not a problem if you're just waiting for that thing to execute. It's just one line of code. But typically you have a bit more code, and then there's this other thing that's called priority inversion, right? So you're not only waiting for that thread, but maybe that thread, it's a low priority thread, so you may be waiting for other threads. And then you don't have real-time guarantee anymore. So you don't want to block. So that's mostly not a good idea. So what can we do instead? We can use an atomic. So we can because it's just a float, we can make it an atomic float, and then we can store it from one thread and load it from another thread. And in this case, the compiler cannot optimize this away. It's an actual load. So if you want to put it outside of the loop, for example, you have to do it yourself in this case. And this is floating atomic, what I call it. That's atomic float. So I'm just going to talk about a little bit more about this. So there's some implications. We use std atomic with floats. So here's the std atomic class. It's the only C++ class that's guaranteed to be free from data races. So you can use it from different threads. That's what it's for. And there is a generic template for it. There is a specialization for integrals, and there's a specialization for pointers. So here's sort of what the standard library provides for you. It provides for you a generic template, which will compile with anything that's trivially copyable. And then there's here lots of specializations for built-in types. And you may see that float is not in here. So atomic float is actually not in the standard library. Yeah. So if you do atomic float, you would be using the generic one. And then there's another one for pointers, which is important here. These are the member functions of statotomic. So you have the simple ones, load and store. Then you have exchange, which allows you to swap two values. And then you have the ones that are called compare, exchange, weak, and strong. And so basically what they do is they check, is the current value equal to the expected one? If yes, replace it with the desired one. Otherwise, don't do anything. And then return a bool whether you did anything or not. And these are basically your bread and butter functions if you're writing like log-free structures. But with the float, probably it's not that useful because it will do a bitwise comparison for floats. And as you may know, if you compare floating point numbers, it's not really useful to do that because they're not precise. Probably with a float, you wouldn't be using them. And then the other thing with floats is you can have, there's a thing like floating point exceptions. So actually, strictly speaking, there is no such thing as atomic float because the operation could throw floating point exception out of an atomic operation. Is that still atomic? Well, this doesn't really occur in practice, so that's not really important. But to be pedantic, strictly speaking, floats can't be really atomic. And then there's this other thing that atomic and log-free are different things. And I think that this is sort of, sometimes people mix these two terms. So atomic means that read and write operations are indivisible. So you never get like in-between states. And all readers see the same value. It's either before or after the write. And it's guaranteed to be free from data races and thread safe. But that's it. So if you lock something with a mutex, that will be atomic. Log-free, on the other hand, means that the read and write operations, they do not block. So there's no mutex lock inside. So what we really want is atomic and log-free. And the thing with atomic is that atomics are not guaranteed to be log-free. That's another little detail in the C++ standard. And atomic actually provides you this function which allows you to check if T, your type that you're using it with, if that is log-free or not. Because if not, then actually when you compile this, the compiler will insert mutexes inside, so it will not be log-free actually. And yeah, what you want actually is to be able to test that maybe at compile time with static assert. Is it log-free for my type or not? And then maybe I can use it for real time or not. But unfortunately, you can't do that because for some reason, this log-free function is per instance. So the compiler can decide that one instance of one atomic type is log-free and another one is not at runtime. That's really weird. It makes sense for some really obscure architectures, but I don't know. So you have to test it at runtime. Per instance. But the good news is that practically all the fundamental types are log-free. So bool, int, int64, they're all fine. Float is fine. Complex float is interesting. Like, depends really on the compiler and the architecture, whether the compiler is able to figure that out, that it can use like atomic instructions for that one. So my MacBook, Xcode can do it. Windows can't, Visual Studio. But if you have anything that's not a fundamental type, pretty much you know that it's not going to be log-free. And then there's this other, actually the only type that's guaranteed to be log-free is that atomic flag thing, but it's more of academic interest, so I'm not going to go into that. And the last thing about atomics is that there are these memory order things, and if you want to know more about this, there was a brilliant talk by Herb Sutter, which is called Atomic Weapons, where he goes into like gory 3-hour detail about how to use them. And basically, the bottom line is never use them. Yeah, bad things will happen. So they're basically to like solve very, very specific performance problems on some very specific architectures. And I'm pretty sure no one here has this problem. So just it's not there. Forget about it. So yeah, this is I think why atomic float is useful and what are the things that you should sort of keep in mind. So yeah, we end up with this code for our little level knob. So it's thread safe, right? It's log-free. It's nice. It's cool. Would you ever actually implement a level knob like that in an audio plugin? No, you wouldn't, right? Why not? Yeah. So it's going to do that, and that's going to be, if that's the level and that's like the audio you're generating, it's going to do that, right? If it jumps, and then you're going to get these nasty clicks. So one simple solution to this is to use linear interpolation, right? So you have some kind of thing that generates like a linear ramp, and then you scale your audio with that. So that's an easy way to do it properly. And we have a class in Juice that's doing that. It's called linear smooth value, that thing here. Takes a template parameter, so we keep using a float. So what it basically does is you set a new value here, a new target value in the GUI thread in this case, and in the audio thread you can do get next value, and this will sort of step up the ramp, and after a few samples, and actually you can specify how many these should be, it will sort of approach the target and then stay there until you change it here. So that's a really nice utility class that's in Juice. You can use it. Here's the code. Yeah, so I've omitted some other constructors that this has. It has like the target value here, the current value, the step, and that's the implementation of set value, where you set a new target value, you compute how many steps you need. Then there's get next value, which sort of, if you're already there, it just returns the target value. Otherwise, it does this countdown and sort of steps up every time you call this, right? So this is super cool. We use this also internally for some audio effects. So these are these two functions, right? Set value and get next value. What's the problem here? Sorry? No atomics, right? So this is actually undefined behavior, if you call it like I showed previously, right? Undefined behavior. What do you do? Well, the problem is that the first example was like you just read, like you assign the value, which is one line of code, and in the other thread you read it. But here we have like a little bit more code and a little bit more code, and they can be interleaved in various ways. You don't know, so you can get really weird garbled numbers if you just use it like that, and it's just undefined behavior, really. And you could insert a mutex here, but we know that we don't want to block an audio code, so we don't want to do that. So what do we do instead? Atomics. Okay, so there are actually 3 relevant parameters to make this work. It's you have the target value, the current value, and the countdown, like how far away you are. And you could sort of put these 3 values in a struct and make that atomic, right? That's one solution. But unfortunately, these are like 3 numbers together, so it's not a fundamental type. It's not going to be block-free. What you can do is you can do like an atomic pointer to that thing and then swap them around. That would be lock-free, but then you would have this whole thing on a heap, and it would make everything unnecessary heavyweight, because then all of a sudden you need to access some heap memory. So that's probably also not the solution. So we need to find a way to have like one atomic value on the stack to make this thread safe and real-time safe. And atomic float comes to our rescue. So this is actually templated for float and double, but we're using this here with the float. So this is one way to do it. You basically, in the set value, which contained previously all that code, I just moved that away. And the only thing I do in the GUI thread now is to store the atomic value, which is just the target value, right? So you have to pick one value that's going to be your atomic thing that is thread safe. So the target value is set here, and you don't do anything else. And then we've offloaded the whole computation into this function, which is called now here from getNextValue. So getNextValue would first check, has this atomic, like safe target changed? If yes, update like the target that I'm using in the other thread, which is called current target here, and then do all the stuff. And if you do it like this, then you're fine. That's thread safe, right? And like a good rule of thumb is always, you should always pair like one store in one thread with one load in another thread, like here, and then that's fine. One problem here you could say is actually you offloaded this whole computation now to the audio thread, right? Because you're calling it here. Maybe that's not good. The good news is that actually on x86 and many other platforms, this float, like atomic load here, would be just a normal float read, like the instructions actually compiles to, so it doesn't have any overhead. So you're fine. but you would still be doing this if check here in the audio thread. So maybe you can get rid of that as well, and then you can call that from like for the whole buffer that you're computing here. And yeah, and then we're there basically. So that's like one example. And with that code, you wouldn't have any performance problems, pretty sure. It would be thread safe, it would be lock free. And that's just an example, like in real life, how to use atomic float to make something lock free and thread safe without really much effort. So yeah, that's what I would do in this case. And that code works just fine. Just an example. Yeah, so summary, no induced still atomic, it's good. It's thread safe, it's lock free. It is defined behavior. It expresses what you're doing stuff concurrently. It's portable. It doesn't impact performance if you do it right. And also there's some specifics if you use it atomic with float. So be aware of that. Probably avoid compare exchange and other things. And as a rule of thumb, pair one store and one thread with one load in another thread. And that's a technique that I find very, very useful if you do simple stuff like that to make your code thread safe and lock free. All right, that's it. Thanks.
Thank you very much, Timur, for naming and shaming some of my own code and showing me how to do it better. Any questions for Timur? Lots of questions. Stop in front.
So the memory order stuff, when you do, if you don't apply the memory order flags to the atomic store of the float,
Yes.
you get a full memory fence.
On some architect, on ARM7, yes. On ARM,
On Intel you do.
not if you do a load. If
No, when you do a store, when you do a store, you
yes,
do,
if you do a store, you get one, but you're only doing the stores from the GUI thread.
It's
so
okay,
the
so you
stores
say-
can be expensive as long as the loads are cheap.
Right, okay.
So yeah, you don't have a problem on Intel with that, as long as you don't do any stores in the real-time code.
Yeah, Intel's fairly forgiving on the load.
So what about the case when your type isn't just float and you are back to that situation where you have, you know, a struct that you want to synchronize?
Watch my CPP-con talk. I have some examples there. So basically, you have to put it on the heap and then do atomic pointers or apply some other strategy altogether.
Cool. Thanks.